Hello, Link 341. Welcome to another lecture on vowel acoustics. This time, we're going to talk about source filter theory. The source filter theory was developed by Gunnar Fant or Font, who was a Swedish phonetician around back in the days in the 1960s. He said that there is a source, right, that creates these complex wave by periodic opening and closing of the vocal folds, and there is filter, which is our vocal tract, that shapes these into certain vowels, right? So these are shaped by the resonant properties of our vocal tract. And this is how a power spectrum looks like, for example, of the fundamental frequency or the source of 150 hertz, whereby the other harmonics are integer multiples of this first one, which is 300 hertz, 450, and so on and so forth. This is what the power spectrum would look like: frequency on the x-axis, amplitude on the y-axis. Yeah, that's basically the source, right? And I'll keep score of this on the board. So we have, as I said, maybe I can write F0, right? Or our vocal folds, which are the source, right? And our vocal tract, which is the filter, also F0. And we'll see what's on the other side of the spectrum. So these are source differences between a male and child voice. For example, adult male voice is F0 is around 150 hertz, right? And child voice is around 300 hertz. So there are so many more harmonics squeezed within these 1800 hertz harmonic. So when they meet at 1200, adult male voice squeezed in 8 harmonics and child voice squeezed in 4 harmonics, right? So that's the difference between source, and those are created by our vocal folds, and those are dependent on F0, of course. Right, so that's our vocal folds. I can also write down here harmonics, right? Okay, good. So we know about the source. Just so you know, voicing on its own would sound like a low-pitched bass, right? What we mean by this is basically, I show you here a sawtooth wave. So this is a sawtooth wave, and this is how you might sound if you didn't have head, right? So you might sound like this, right? Maybe not with the same amplitude, but different amplitude, because here we have the same amplitude. And if I analyze it to spectrum, I'll see that the amplitude, oh, actually it's not the same, actually, nice. So the amplitude is not actually the same, and this is what you would sound like if you didn't have head, right, on, which is a bizarre concept, but we can just visualize that, right? What happens is that the source works, right? Imagine if you have just vocal folds, and those are vibrating, and because it's an open air, right, out there, they will be dampened, their intensity will decrease, and they will sound something like this, but the frequencies, the harmonics will remain the same. Okay, and this was a sawtooth wave of 150 hertz fundamental frequency. So it's somewhere here, 150. Then here should be 300, and here should be 440, and so on and so forth, right? Yeah, 450, right? Yeah, that's what I want to say. All right, vowels don't sound like this because the source gets filtered by the vocal tract. So what's important for us is that we have the head, right? And okay, we have some kind of shape of our vocal folds and our vocal tract. Actually, this is our vocal tract, right? And harmonics are poured into the vocal tract from the source, right? This would be source, and this would be filter. Okay, so the filter, they're filtered, which means that some will be amplified, some will dampen, right? So for any particular vocal tract configuration, certain frequencies will resonate while others will be damped. Imagine this, you can imagine or just visualize this as a natural variation or environmental selection. For example, if you have crops or field of certain crops, some crops will, due to a lot of rain and sun, will develop, right, will grow more than other crops who didn't get this water and sun. And imagine that this happens to our vocal tract. What happens here is that, for example, if I have some kind of a neutral vowel such as right, schwa, oops, what am I doing? Schwa, right? Schwa vibrates, or its formant frequencies, resonant frequencies, F1, are at 500, F2 at this number, and F3 at this number, which we said were, F1 500, F2 would be F1 times 3, right? And pay attention, this is only valid for schwa, which is our neutral vowel, which is how the standing waves are resonating when we are not shaping up our vocal tract, when we're producing right, in this state of neutrality, right? And F3 would be F1 times 5 in this case, but not for all vowels, because we then shape our vocal tract and former frequencies change. What we need to understand here is the following. If I had a tube of 70 centimeters, which is the usual length of our vocal tract, and I'm producing something like this, if I want to produce something like this, I need to amplify or hit those, or amplify those frequencies at 500 hertz, at 1500, at 2500. If I amplify the frequency at 1000, right, nothing will happen. It will not resonate, right? And I won't reach this resonant frequency. So that's why it's important to understand that filter is okay, where is it? It escaped me. Here it is. That filter depends on the vocal tract, and these are, while source has F0, and harmonics, filter has resonant frequencies or formants, right? Okay, we know this. We can also say, because F0 is fundamental frequency, F0, then after 0 goes 1, F2, F3, and so on and so forth. But for now, we are concerned with just the first two in general. All right. Right, let's move on. Okay, I'll do this, maybe. Okay, so the graph represents how much the vocal tract would resonate for sine waves at every possible frequency. The output of the source plus filter is something like this, right? Or better to say something like this. So we have a source function, or glottal pulses, or our harmonics, and they are at certain amplitude or certain decibels, certain loudness. They are also at certain frequencies, right? But because of our vocal tract and the shape of it, some will resonate more. What happens is that these here are dampened or damped, and these here are amplified, right? and these are approximately at 500, 1500, 2500 for our neutral vowel schwa. This is what it looks like for Steve's, Dr. Winters's a vowel, which is a neutral vowel, so it's around 500, at around 1500, at around 2500, but the rest of these are damped, right? And output for E will look differently. Why? Well, because we are shaping our vocal tract. This vowel for E, as we wrote on the in Word or in PowerPoint, on the whiteboard, blackboard, wherever you were, in person or virtually, we wrote on the board that F1, if F1 is lower, it's counterintuitive, we have a higher vowel, which is E. And if F2 is higher, we also have a frontal vowel, which is E, right? So F1 is here very low, and F2 is much higher. It's not anymore F1. It's not anymore that F2 is F1 times 3. No. This time it's not like that, because we have so many harmonics squeezed between these, and these are all damped, right? But F2 is at around 2500. Okay, and this is what it looks like. So this is power spectrum on to the left, and on spectrogram, this is what these would look like. These three harmonics that are also resonant frequencies, right? So, yeah, different vowels will be shaped. So harmonics will be shaped to be amplified accordingly, right? Whether we want to say or E, it depends, right, on us, and these harmonics that are poured into our filter will be filtered in a certain way. These reflect changes in the shape of the sound filter, which is a vocal tract, and the vowel spectrum for E would be this. So at around
heed.
This is a Bruce Hayes, I think.
Heed.
Some will be here at around, let's say, 300 and something. This one will be at around 2000 or 2500 or something, and so on and so forth. Okay. Now we understand that source and filter are independent of each other. So basically, if I have source here as my vocal folds, I can manipulate those vocal folds quite independently from filter, right? I can have E at different fundamental frequencies. This is what it looks like to have at different pitches. For example, at a standard, right, at certain pitch, 100 hertz, we can squeeze in. So if this is first harmonic, 100 hertz, 200 hertz, 300 hertz, 400 hertz, and 500 hertz, and this is the fifth harmonic that would be amplified, right, in this case. In this case, when we have a higher F0, there are 4 harmonics squeezed within, right? And around like 4th, 5th harmonic will be amplified. In this case, there are even fewer harmonics squeezed in because of higher F0, right? But, and then therefore the 3rd harmonic would be amplified, right? So this shows that appears at different pitches. All right. We have a good representation of our vowels, and I'll try to record for you. Why not? Okay, let's see how that goes. Now, I have a certain representation here on the top, and that's waveform, and on the bottom is spectrogram. I have spectrogram settings, and I'll leave them to standard settings, just like on your computers. So this is what it would look like. However, if I want to see harmonics better, I will tweak my spectrogram settings. What I'm going to do is reduce the window length, that reduce the level of detail that I need, right? I reduce it to maybe 0.03 or maybe 0.06. I like 0.06, and I even lower down the intensity to 50 maybe. Let's see what it looks like. It looks like this. It shows to me harmonics. So my harmonics, first harmonic is around 135 hertz. Second one should be the integer multiple, right? So 260 or 270. Third one would be whatever, 400 and something, and so on and so forth. And you can see here that around the 1, 2, 3, 4, fourth and fifth, there is amplification, right? So there should be somewhere be my first form and frequency. And around the second one, okay, there is an amplification there at around, let's say, what is this? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So around 10, 11th frequency, right? And here should be my third one, right? But let's say I'm concerned with the two of these. And as I said, this neutral vowel should be around 500 hertz, the first harmonic, and then F1 times 3 should be around 1500, so somewhere there, right? And the third one, maybe lower a little bit, but you get the point. It's the variation in speech is huge, so we cannot always pinpoint that. But what we can do is have a analyze spectrum, that is present these harmonics in a spectrum which is power spectrum. This is what it looks like. I'll increase it a little bit and see what happens here. So this is my first harmonic, second, third, and fourth harmonic is apparently the most amplified, right? It resonates, my vocal tract resonates at that level, and therefore that harmonic is amplified. And then I have say fifth, sixth, seventh, eighth, ninth, 10th, 11th. I guess at 11th would be F2, and F3 would be maybe further down the road, like somewhere here. Yeah, somewhere there. So I can maybe, oops, what am I doing? Do the following. Let me draw a little bit. So right, okay, cannot see, maybe I cannot see this one is at the end, doesn't really matter. I have the two of these, and the first one is F1, second one is F2, and the third one is somewhere there, here, like F3. Oops. Difficult to draw, sorry about that, but F3, right? Okay, and those are my harmonics of my neutral vowel, right? But for other vowels, I will have different harmonics. Okay, this is done. I'm okay with that. Let's now record E, maybe. E. All right, let's see what that looks like. I'll immediately send it to spectrum. Okay, my first one is here, second one is there, third one is there, right? For E, so this is good for taking a look at harmonics, right? Right. But if I want to take a look, let me go back to my neutral vowel. Oops. If I want to take a look at formants, I'll need a different representation. This is what we call a narrow band spectrogram. So the formants here are less distinct, but harmonics are much more visible. So this one is good for harmonics. I have a wide band spectrogram, and I will go back to my prod and go back to my vowel here and go back to my spectrogram settings. Spectrogram settings should be standard, right? And I click OK, and now I have much darker bands here, right? I can see better where my first formant lies. So my first formant lies, I grab the middle part and grab this chunk here and put the cursor over there at 576. My second formant lies somewhere here, maybe, yeah, maybe over there at 1473. Okay, those are my two formats. And the third one would be obviously here at 2810. Right. For my E vowel, I cannot see very well on my power spectrum, but I have a spectrogram. What I can do better maybe is decrease this to 50. Let me see what that, yeah, might make it better. Yeah, so for this one, there are a lot of dark bands here. Yeah, but I assume it should be somewhere here, in the middle at 420, and the second one should be somewhere here at 2654. And that's what I get when I take a look at this one, right? These ones, right? 325, 100. So a huge distance between these two, right? At E, for E vowel. So wideband spectrogram shows formants better, but not harmonics. And that's why I'm going to write here narrow band spectrogram and wideband spectrogram. Okay, right, so we understand this, hopefully. Okay, when you are deciding where the formants are, what you just need to look at are these dark bars, right? And this is how you will indicate this is F1, F2, F3, and you have that for your homework as well. So this kind of wideband spectrogram shows formants better than harmonics. And even in wideband spectrogram, we can see glottal pulses or voice bars. If the frequency is low, when the fundamental frequency is low, these voice bars will be spread, a bit more spread. But if the frequency is high, they will not be so spread. However, this is not so important for you. Yeah, this is a little bit, these are a little bit spread because of low frequency, so you can see them clearly. So you should just know these are voice bars or glottal pulses. I may also write those here, right? Oops. Voice bars. They are also dependent on your vocal, on your source, on your vocal folds. Yeah, glottal pulses. And here we can say dark bands, right? Horizontal dark bands. So you should pay attention to these horizontal dark bands, which are dependent on your filter, right? Vocal tract. Okay. I had a nice question, I think, from Emily, who asked me, well, the harmonics are dependent on fundamental frequency, but what if fundamental frequency changes over time? Well, this is what it looks like if we change it over time, right? If we change the source independent of filter, harmonics will also change, right? This was nice. This was good. Well done, Dr. Winters. I'll try the same thing. Let me see if I can manage. Okay, so I'm going to produce in different pitch. Let's see whether that worked, but generally you can see that it's that these dark bars are rising, right? And if I maybe tweak my spectrogram settings a bit, yeah, you can see how they are. I actually started from here, right? And they are more apart because the fundamental frequency increases, right? So they become integer multiples at these particular points in time of the fundamental frequency. That's how you can change source independently of filter. But the flip side of it, and I cannot do this one, okay? Flip side of it is you can change filter independently of the source. And we said for this guy who is doing throat singing is amplifying certain harmonics. So he's changing the harmonics, but the frequency, the fundamental frequency remains the same. Right. So these two are independent of each other. And more relevantly, in diphthongs, the filter changes. That's important. So when you have a diphthong, the filter changes while the source can remain at the same F0. So if I have a vowel like this one, this is E, everything remains the same, right? There is no so much dynamics there. My form and frequencies are the same at this level, right? But when I have a vowel such as Boyd, let's see this vowel, my formants or my filter is shaping the harmonics, and at certain points these will be amplified at certain points in time, so I'm changing the filter, right? There is a lot of dynamics. And as we said, O is a back vowel, so it will have low F1 and low F2, right? But E will have low F1 and high F2, right? It will be fronter. And this is what it looks like for
Boyd.
For a speaker, female
Boyd.
speaker.
Boyd.
Right? You can see here very low F1, then rising F2, right? And if we check out the narrow spectrogram, oh, this one,
Boyd.
let me tweak the spectrogram settings a little bit. We can see that this harmonic F1 pretty much remains the same throughout, right? At around 400, but the second harmonic here is amplified a little bit, and then the second harmonic here rises, right? It's not anymore second harmonic, it's who knows which, right? Like, let's say 15 harmonic that is being amplified. And that's important to understand, that the filter changes while the source can remain at the same F0. So to conclude our lesson on, okay, I'm looking for my document here. I think I have everything written down almost. Almost, maybe not pitch of the voice, that one I forgot, but okay, I will write it down now. Here it is, right? So I said pitch of the voice and voice quality. Yeah, maybe not voice quality. Voice quality should be vowel quality. Sorry, vowel quality. vowel quality. Here would be voice quality, or timbre, but here would be vowel quality rather than voice quality. So we can change the vowel quality with this one, right? With our filter. And we wrote all of these, I think, so we're good. I can just make an analogy here between the strings. So strings would be source, and body of a guitar that has certain shape and resonance would be filter, right? And as I said, a big problem is dynamics. For example, even for this one, hod, the vowel changes throughout the time. It cannot be all the way consistent, so vowel formats are typically not steady state for a very long time. So you have to pay attention to where F1 and F2 are at these points. And with musical instruments, we can only change the frequency of the sound source. That's important to know. That's why we have an orchestra of all that combines all different musical instruments, because all these musical instruments have their own source, they have their own filter, but what we can only change is the source, right? We can only tweak a little bit their tonality or tone, the pitch at which they're played. Timbre is a musical term for quality of a sound, right? We always have this voice quality that is characteristic of us, and that's because of our vocal tract shape and our vocal folds shape, right? Our vocal folds duration, length. Timbre is is a musical term for the quality of a sound. That is its characteristic resonances, and you can compare the same note played by a trumpet versus a violin. They would sound differently. In speech, you can independently change both source and filter frequencies at the same time, like changing the size of a piano as you press different keys on a keyboard, right? This makes the acoustics of speech at least twice as complex as the acoustics of music. Yeah, and that's the moral of the story. It is complex, but hopefully with the source filter theory, now we understand more about our vowels. Yeah, thank you and see you soon.